So in this video we're going to talk a little bit about the forces acting on a magnetic field. If you have a charge moving through a field, you will have a force. We need to calculate a few things. We need to, well, first of all, calculate the force itself. In order to do that, we need to know the charge, the speed, and the field. If there is an angle, that will also affect it, so we can use the sine of the angle, and this takes us to our force formula. F equals QVB sine theta. If it's perpendicular, sine of 90, which is good, sine of 90 is 1, you can just ignore it. You can just write QVB only, because sine of 90 is 1, doesn't make a difference. If it's parallel, that's a problem. If there's a parallel, then that means the angle is 0. The sine of 0 is simply 0. That means the whole thing, there will be no force. So essentially, there is no force if there is no charge. If it is stationary, not moving at all, that's a trick that you might find in an exam. And if there is no magnetic field, there will be no force in those cases. Okay, if you want to find the value of this, you can go ahead and solve a question like this. I can quickly try that with you right now. Probably don't have my calculator to hand, but we can check this here. If I wanted to find the force of each one, you can do F equals QVB sine of my angle. So Q is a proton. We know protons 1.6 times 10 to the minus 19. We have memorized this because we've used it so many times. Multiplied by the speed it's moving at, which is right here, 5 times 10 to the power of 6. Multiply that by B, the magnetic field, which we have here, Tesla's, 12. And the angle we have is 30. So I'll times that by sine of 30. And you put that in your calculator, you will get your answer. 90 degrees, exactly the same numbers, you put everything in, but sine 90, and you will get a new answer. Over here, the angle is 0, so there is no need to even bother trying to calculate. The force will be 0. So there are other possible units for T. If you rearrange that formula that we have over here, F equals QVB, change it to get B, you can have these formulas here. This one we'll deal with later on. This is when we're using different formula, but this one is the one that we will deal with right now. You have your F equals QVB. Changing that to get B, I'll do B equals, take these two to the other side, F over Q and V. I'll divide both sides by Q and V. And the unit for F we know is newtons, and the unit for this one, Q, is coulombs, and the unit of V is meters per second. Okay, this comes from the lib formula. We'll deal with that when we come across that one. Right hand rule, so we can use the right hand rule to figure out the direction of the force that it's moving in. We spent a lot of time working on this as well. Our direction looked like this. We're using the rule. For protons we will use the right hand. For electrons we would use the left hand. So let's bring this out over here. So using my proton over here, I can say that my V will be the direction of my thumb. I will say my B is the direction of my field, and my F is the direction of my force. So in this case, we have the B pointing towards me. I have my V going to the right. My force is acting down. Let's try one more over here. Let's say that we have my B pointing to the left, so I'll take my hand and I will point it to the left, and my V is pointing up like this. V is up, and for my proton it should be like this. So B to the left, V is up. This is out of the page. Out of the page. Very nice. Last one over here on the right. Let's see what's happening here. B is pointing in, so my fingers will point away from me. Thumb is pointing like this, and then my middle finger is pointing to the left. If you have an electron, we will use the left hand. That's the only time we're ever going to use our left hand, is if we have an electron moving. If you use the right hand, it will be the opposite. If the right hand says left, it will be to the right. Or you can just use the left hand, and you'll get the same answer. Okay, so looking at this here, 3 objects enter a field. You have a negative, a positive, and a neutral charge. Neutral we know does not get affected, so it will go straight. If you have a fuel pointing into the page, you can see that the B is going in and all three are going up to start with, like this. The force on my positive charge is pushing me to the left. The force on my negative charge will be the opposite. It will push me to the right. You can check with the left hand on that because it's a negative charge. So there are three situations that you will find yourself in. Case 1, when B and V are parallel. When the speed is going in the same direction as the field, it is unaffected because the angle is going to be 0 or 180, both of which will give you 0. So that means it will not be affected. The second case is when you will see that it's perpendicular. So F equals QVB, as you know, and sine 90. And it will end up going and going and going in a circle because no matter where I stop, the force is always pointing inwards. No matter what I do, whichever way I go, the force is going to point inwards. So you will have a little circular motion here. It will just keep going in circles, as we found in the simulation. So for grade 12, what you need to be able to do is find the radius of rotation. So I'm going to explain these things for grade 12, and I'll quickly show you that now. So grade 10, you do not need to watch this part of the lesson. So for grade 12, what you need to know is find the radius of rotation. So we know it is going in a circular motion. You will maybe need to calculate the radius. So we're going to bring back stuff that you learnt from grade 11, which is when we were doing centripetal forces. If you remember the rule, mv squared over r. If you make mv squared over r and qvb, we can make them equal to each other. So mv squared over r equals qvb. You can actually use this default form to calculate for anything, to find the speed, to find the radius, even to find the mass. You can do. But to focus on the radius, which I've mentioned, we will just rearrange this to get r. So we will have r equals mv over qb. That's how we will find it. We'll take the r across here, then we'll take the qb over here, then we'll take the v up here like that. Oh, well, actually that v will come down. It will cancel with the v squared. So you'll have only one v left. No need to worry about rearranging. There's the formula, mv over qb. Nicely done. Okay. And if you were to sketch a path, of course, you will know that the electron might go in one direction because this is pointing out. You can check with your right hand rule. The proton will go in the opposite direction, and you will see that the radius is bigger because the mass is bigger. Bigger mass means bigger radius. According to our rule, mass is bigger, radius will increase. This is used in a mass spectrometer. If you wanted to see the mass and the charge of ions, I should say, it lets you know if you have a sample of a material and which different isotopes you will have, because different isotopes will have different numbers of protons, different numbers of, not protons, electrons. It will have, well, different charges, right? So then if that has a different charge, you will see, or a different mass, you will see that they will take different rotations, different radii, different radiuses, and you can separate the each different isotope and figure out what is what, which is quite useful for scientists. And the third and final case, which is not so important, you'll just know that if you have an angle that's less than 90, it won't be a full circle because it's still kind of moving forward a little, so it'll be in a little helical motion. It'll be like a little spiral. It'll still go forward and it'll still try to rotate, but it will still keep moving as it does. So you'll see a helical motion like this.